So, did you have a chance to look at my lectures from last year? The first one. Was the second one around?
It's there.
Oh, it's there. Okay, okay. Pretty long, aren't they? Boring. No, not too boring.
No.
Makes sense.
You follow it amazingly well. What you said last time.
So, any comments or questions you have about last time, this assignment, this lecture? I'm going to cover some of those things just a little bit again, but.
Last time you said something to remind you about Darth Vader or something that you
Yeah,
didn't
Darth
mention.
Vader helmet.
Darth Vader. Oh yes, Darth Vader. That's coming. That's coming next week. Sorry, but next week is going to be so exciting. Yeah. Well, this week's exciting too. But I mean, anytime I get to spend with you guys is exciting, right? Well, for me. I don't know about for you. Okay. Any other inputs about the homework? All right, well, let's tear into this. I'm going to give you a little review. This is going to be a quick brush through where we've been so far. Definitions, right? You guys are up on definitions.
Yeah.
You know all those. You also know what the 4 elements. Got that down. All right. We talked about these models, right? Got that down. And the summary of that. We've got to characterize all these goodies in here, the human, tool, and the task, and the connections between them. Not gonna have time to do that, at least from my side, but hopefully other guys will be filling in so that you can come up with those characterizations. We did talk a little bit about these different layers in the model, right? And about the 6 senses, not the 5, but the 6, including
20-something.
Sorry, and then we added more, right? We added all these others that are there, and the aggregation of those senses that they're sort of worked together. And do you guys try out this kinesiology thing anymore? To prove that it would work, that kind of thing. Did you try it out? Yeah. And?
A bunch of other people.
Did it work?
Kind of mixed.
Mixed?
Yeah. I think people were getting tired of me.
Ah, okay. Did you reset them and make sure that their chi was reset before you went between things? Because that's important. If you don't reset, you get mixed readings. Yeah.
I met one chiropractic and he was using the same method.
Aha. Yeah.
Yeah.
Mm-hmm.
I don't know if it's like optical in that area of that field, but
Mm-hmm. Yeah. Yeah. It's alternative medicine, the naturopathy and the osteopathy and the chiropractic. All of those people use some of these techniques. Okay, remember we talked about the mapping, right, of all the nerve endings in the sensory end organs up to the brain and how that's mapped. We talked about perceptual organization, how this is put together so that we're three-dimensional. We have this duality in our visual system. Just a little more on that, by the way. If you look at the organization of the receptors, I mentioned this, but I didn't show you this chart. The receptors, here the density of receptors in the retina of the eye. What you see here are the rod receptors in this gray area here. And what you see in this checkered area are the cone receptors. Now the cone receptors give us our highly detailed color vision, right? And but you see there's still some cone receptors way out here in the peripheral retina. Look at this. It's going across, here's the fovea centralis. So it goes out to about 70 degrees here and about 80 degrees there. It's amazing, the instantaneous field of view of the eye. It actually keeps going out further than that. But look at this little spike here. That's in the fovea centralis. That's where we get our highly detailed color vision. That's only about 2 degrees. And so we have to have these saccadic movements of our eyes in order to position that over the areas of interest. But if we look at that, as I'm looking at this monitor, or sort of a normal monitor, all we're pretty much stimulating is this. See that little gray region there? Which means that we're basically throwing away all this other stuff in terms of a channel to the brain. And that was the point I was trying to make here. The PPD, by the way, is a personal panoramic display. I will be talking to you about next time. Okay? So, in these two receptor regions, both the rod and the cones are processed at different places in the brain, not even in the same place. And as I mentioned, these rod receptors do a lot of things in terms of optical flow, of postural control, things like that, and tells us where to look. Whereas the fovea centralis and the cone receptors tell us what's there once we look in that direction. Okay, we talked about two brains and that we work on mental models that we build and that we're all different. Remember the old exercise that we really organize our world a lot differently. And then we talked a little bit about some of the cognitive things, cognitive functions, and how we have this model up here that we build, our memory, based upon the experience we've had in the past. And then, of course, working back in the other direction are the psychomotor considerations that relate to this transduction path. So in the end, we summarize and say, okay, this is what we understand about humans, if we want to make a list. And that the quality of the transference of data to become information, this thing that goes in between here, the bandwidth, is really a function of everything. It's a function of the human capacity as well as the tool capacity to deliver and to interact. So you can't just say it's one thing. It's really all of this. And then when we look at what we have today in terms of traditional interfaces, they're all wrong in terms of really mapping and creating this great impedance match with the human. And for these reasons. So we're golden there, right? We understand that we've got limitations and problems with existing technology. But today we're going to talk about how to get rid of this bottleneck. Now, a little bit more went into how to design interface, and that going to the fundamental systems engineering principles, you have these 4 steps. But what is the first thing that you ask when you are trying to design an interface?
What's the task?
What is it supposed to do? For whom is it supposed to do it? How well is it supposed to do it? And only when you get down there a good distance, you say what it is. That's usually not what happens. When we were designing fighter cockpits, so we get this new analysis, or what is called this document from the operational commands, saying, okay, we need a new fighter airplane. There's all those bad guys out there. This is what they have, and we have to build something to counter that threat. So usually what happens is you look at what are the latest engines that have come out, what's the latest materials come out, what's the latest electronics coming out, and you just put them all together and you have this new high-tech airplane. And so when you get down to drawing a block diagram of what has to be in there, you say, well, we need a navigation system, we need our radios, we need our energy management, we need our air data, and then you just go through this whole thing like you have 100 years. Well, not quite 100 years. And so you come up with this system design. That's not the best way to do it. The best way to do it is say, okay, what is it supposed to do? What we're trying to do is deliver energy from point A to point B. And in between, there are these guys out there that don't want us to get from point A to point B. And this is what they are doing to prevent us from doing that. So how would we design a system to do that? So when you start thinking that way, getting down to the fundamentals, and then you say, okay, what helps us get from point A to point B and deliver this energy there? You say, well, wait a minute. We have two boxes in the airplane. We have the flight control system, and we have the weapon system. Flight control system is to point A, point B, and the weapon system is to release all this energy. Why are they two different boxes? That doesn't really make a lot of sense. And we found out when we started coupling the navigation system into the weapons aiming systems, it was transformative in what you could do in the airplane. And so nobody ever asked that question before. We just assumed these things were all separate. But when you put the two together and you add communications, all these kind of things into a more integrated system, it makes a lot more sense. So this design cycle. But for interface design, you have the commandments. If you follow the commandments, everything will be peachy keen. And of course, this idea of a persona. Because you can't second guess everybody, but you can come up with one person. And the object then of the design is you want to please this one person. And you know this person very well. And this helps a lot because that person now is basically taking the guys over here and putting them into your head so that you can design for that person and use them in the design process. Okay, so that's where we've been the last 2 weeks. Now we're launching into the sort of the machine side of human interfaces. Now we won't get through all the machine stuff today, but we're getting into a little more machines on the 4th week and applications in the 4th week, and especially some of the ways to do the evaluation of the goodness of these things. We started a little bit with that, but we're going to continue that. Okay? So let's look at the machine or the tool side of human interface technology. So these days, there's just an incredible demand for interfaces. I mean, it didn't used to be that way. It used to be that, pretty much, as I mentioned before, we got a telephone, and whatever the Bell system said is a telephone, we accepted as a telephone. And but now people are beginning to look at what's on the outside, the face that you see in interfaces, and the bar is going up in terms of expectations, in terms of functionality, and then you have things that are happening like the Wii that have changed the whole dynamic in the way that we play games with computers, where we're now talking about gestural and whole body interfaces rather than just using our fingers and using our eyes and things like that. So I sort of showed this to you before about God and Peter, talking about it. The interface is more than just the hardware and the software. It gets into the cognitive side. We've already been there before. But look at what can happen if you do it right. The empowerment that comes here. And this is based upon experience, personal experience I've had, that this is what can happen. You can do an amazing job of accelerating the ability to learn. This is especially true when we get into virtual reality. Amazing in terms of the processes you can learn and what you retain. You generally don't forget a virtual world. If it's truly an immersive virtual world, you never forget it. Another thing is it can awaken the mind and body. Again, you'll see some of these applications later on of how that happens. Rapid assimilation of information. The way that we organize and portray information, taking into account the organization of our sensory, perceptual, and cognitive subsystems means that we can get higher bandwidth to the brain and from the brain by taking advantage of the way people really work. We're able to move our minds to other places and other times. And I'll show you that also in next week. Providing access to people who don't have the capacity to do certain things by being able to transform the way things are activated by using other modalities that you wouldn't normally use for that. And creating whole new levels of human experience, like walking at the speed of light. What would happen when you walk at the speed of light in terms of what you see? I mean, you can think about it from the books, the pictures, and things like that. And what if you're walking backwards? Or what if you're looking to the side when you're walking at the speed of light?
Meant to be something with time travel.
Well, there's amazing distortion that takes place, as we understand from relativistic mechanics. But once you've walked at the speed of light, you never forget it. And it helps you understand some of the principles behind the mathematics. I mean, you look at the mathematics and you say, well, yeah, I understand that, but what does it mean? So what? So those kinds of experiences we can provide. Shrinking yourself to 1 millimeter high and visiting places with different scale factors. So there's all this cool stuff that can be done with human interface technology, but you know, we've got to be careful about it, because let's look at what's happening today. We have this amazing mobility here, but now the screen is even smaller. So we're throwing away even more in terms of human capacity. And when we're now trying to interact in this space, rather than at least in this space, when in fact the real world's like this. So how do we solve those problems? And there are even more demands. One of them is coming with portability. But think about this. There are a heck of a lot more things out there for us to tap than what we had before, in terms of this enormous knowledge of the world that can be represented. We also have this increased consumption of bandwidth. Just like memory in your computer, you're going to suck it up, because now the apps are going to suck it up or whatever. Don't worry, you're always going to run out of memory in your devices. And the fact that now we're streaming multimedia, guess what? We're going to be bringing down the network as it exists now. I just gave a talk a couple of nights ago over a Snap, and you know, they're thinking ahead a little bit about what in the world are we going to do while everybody's watching in real time movies and at HD quality, streaming real time. A lot of things going on with social networking that didn't exist before. Instagrams and Twitters and twits and tweets and Facebooks and all this kind of stuff. Now more and more stuff that we would normally have on our machines up in the cloud. All my music is up in the cloud now, so that all my machines, all my gobs of iPhones and iPads and laptops can access that, but it requires bandwidth to do that. We're expecting more and more now of, I mean, have you tried to go back and watch a low definition, standard definition program on TV?
I tried to use the VCR last week.
Yeah?
I couldn't get it to work.
How soon they forget.
What was that saying?
I say, how soon you forget, right? Yeah. Oh, well, I have a little story to tell you about my wife. So we had a regular TV, you know, just, and one of these big jobs, you know, about that deep and big pictures, you know, fairly big picture on it. And so I had bought one of these for my lab. Actually paid for it out of my own pad, because we were going to have Helen Clark come to visit. Helen Clark's the former Prime Minister of New Zealand, for you. I think Oz guys wouldn't know about it, but Anyhow, she was visiting the lab in Seattle, the HIT lab. But Mark and I were down here. So what we did is we wired up this life-size system. We had a life-size system up in Seattle at the HIT lab. And so we visited with the Prime Minister from his room through high-definition television. Really cool, really. But then it was over. And then we boxed that thing up again, this TV, and it was sitting in a box in my office. And I thought, I will take it home. I'd already talked to my wife about this. She said, I don't want one of those. I don't want one of those big things because it's just too big. Don't need it. This is fine. So I told her, I went home one day. Actually, I did it when she was out. I moved it in and put it there. And I said, it's, we own it. Let's just put it here just to see how it works and things like that. I don't want it. It's too big. She's sitting about 10 feet away from this thing. And I started bringing up a few programs, high-def programs, and especially the football game. She's a rabid basketball. And then over a period of about a week or two, I noticed that she wouldn't look at any program. She kept looking for the high-def channels, and she wouldn't watch any of the regular ones anymore. And now, if I tried to take that thing out of there, she would wring my neck. But that's what happens. We get seduced and overcome, right? Yeah. Okay. And then there's this notion of the experience economy. Gilmore and Pine wrote a book called The Experience Economy. These are two guys that are trying to sort out what's going on now in terms of our world. You guys especially. If you ask most of guys your age what you're really looking for, what do you really want right now, it's not things. It's experiences. It's like experiences, travel, places to go, things to do. Whereas in my generation, it was all about getting that car and that second car and about a boat and a big house and all this kind of thing. Not that you wouldn't be interested in those things, but it's not the primary thing anymore. You go out on the Routeburn track here in New Zealand, and you see people from all over the world there. I mean, from all over the world, literally, on the track. You meet them, and you say they're young kids, things like that. And I say, well, what brings you here to New Zealand? So, well, we're on our way around the world. What do you mean? He says, well, we both had jobs. We sold everything we had, our cars, everything, and we're taking a year off to go around the world. Well, what are you going to do when you get back? Well, we'll work another 5 years and then sell it all and go do it again. I mean, really, it's amazing what's happening in this day and age. That's more important, seems to be more important than the things. So this will impact, the future of technology and the future of the way things are designed. So here we have, basically a whole gob of interface technologies. Now these are ones that we actually see, where we see this part of the interface, in terms of visual displays. Here's a contact lens, which is a display that you pop into this is actually invented at the University of Washington. And here's a pico projector, laser projector. I'll show you one of those, by the way. This is based upon some of my technology. And controllers and hearing aids, the Connect, the emotive interface just measures brain waves and controls things. So here are, examples of interfaces that you would see. But there are also parts of the interfaces that you never see. Like, how does all that communication take place? What are the guts that are inside your machine? This is actually an antenna that's inside, an antenna RF amplifier that's inside your cell phones. Accelerometers that are in there that tell you the orientation, gyroscopes. You have the code, you have the microprocessors. All these things you never see, but they're still part of the interface. Without those, I don't care what you have on the face, it isn't going to work. So you have to take all of that into account. So how do we think about it? How do we think about this whole business of, we understand now about the human, how do we make the technology come together to match it? Well, let me suggest that we first start off with a taxonomy of how to think about technology. Now, what do I mean by taxonomy? It's, if you look at the traditional definitions, it says a practice or principles of classification. Or, and classification is allocating things into groups. Basically, my definition of this is really just a structure for thinking about things. So let's look at a taxonomy for these experiences that we're talking about. So let's call this the normal experience. Here's the world over here, and here's the human over here. Whoops. And generally, when we're in the world, we have this, this closed loop. We have things, we have these photons coming in, we have these mechanical vibrations, things like that. And then, of course, we interact with things. We control things by movements of our hands, by speaking, things like that. So this is a normal experience. And here's a direct interaction that we have every day when we eat. We're pretty much using all of our senses, aren't we? Pretty much all of our senses. And all our psychomotor mechanisms. We don't have to use speech, but I mean, generally, that's if we're talking to our, our companion here, we might be using speech. Well, anyhow, that is direct interaction. Now, when we talk about technology, where does technology fit in this? Well, it's some kind of mediation that goes between the world and us. Now, we may still have direct perception and direct action to the world, but this box sort of fits in between. And this box itself has ability to sense, an ability to act in the world, to close this loop. And of course, we have the ability to close the loop with the box. And what the box does is it sort of can sense or transmit, it can filter, record, simulate. All of those things that this box can do. So there are all kinds of synthetic experiences we run into every day. For example, the cinema. What the cinema really does is take our eyes to another place and another time. And our ears too, for that matter. A television actually does this sort of in real time, although a lot of stuff we watch on television is recorded. Virtual reality, what does it do? It lets us be in a place that doesn't exist. And we'll talk about that a lot more here coming up. Flight simulation, same thing. Simulation lets us learn to do things that we need to know how to do before we go out and do the real thing. Teleoperation lets us to do the same thing from operate things from a distance. By the way, I met a guy that was a mining engineer, mechanical engineer, works for Rio. What's the name? Yeah, Rio Tinto. There in Australia. One of these amazing mines. And they have this conveyor belt in this mine near Parks. There's like 5 kilometers long, a conveyor belt, way down into the ground. And oh, by the way, there's nobody down there except these machines. And they're operating machines from above the ground. And they even going in there with robots to repair that conveyor belt. But they can't stop it. You can't stop the conveyor belt, because if you stop the conveyor belt, getting it started again, and what you lose in terms of production is huge. So they operate these robots that go in there, and actually when there's a bad bearing on one of the spindles in the conveyor belt, they go down here and they put that robot in there, and it inserts a sort of an auxiliary spindle in there, so it'll lift the things up again while it repairs the other one, and then lets it back down again, and so it can keep going. That's teleoperation, doing all this thing from remotely. And what a great idea to get the miners out of the mine, because it's not good down there. Then there's micro teleoperation. One of my friends, close friend of mine, and fellow inventor, actually has developed a robot that goes inside the eye for vitreoretinal microsurgery. And there's this little guy that goes down and is actually driven by a little fiber optic and things like that. It goes down on the surface of the retina, and then you can actually see from that direction. It's like you're inside the retina, and you're looking from that perspective. And by the way, the retina is frangible. It's like wet tissue paper. Very easy to tear. But what happens is sometimes collagen material grows over the top of it, especially with babies who are born with too much oxygen and things like that. And it pulls away the retina from its nutrient source in the back of the eye. And it's what we call a detached retina. And so the only way you can do it is either laze it back together, but you have to cut away this collagen material. Well, you have these little weed eaters that go in there, and weed whackers, and go in there and cut away this collagen material. I mean, we're talking about something in scales of a few millimeters that this is happening. And but you're there. You're inside the eyeball, sort of driving around doing this kind of stuff. That's micro teleoperation, scale factor. Telecommunications we know about. Augmented reality you guys know about, where we're combining the real and the virtual together. All these are synthetic experiences. Synthetic sense. A synthetic sense is where you're able to see a sound or to hear a face. One of the things we were doing a few years ago is working on a synthetic aperture radar, or a microwave. Actually, the microwave, in this case, is a microwave landing system for an airplane, where you use really short wavelength radio waves, like a radar, to image what's out there. And one of the things we found out is that in the circuitry of this radar is that there's one stage of it where actually the information that contained what was out there in the world was in the spectrum of the audio spectrum. So what we did was said, hey, that's pretty cool. This is this little antenna that would sit there and move back and forth. So we just took it, brought it in the lab, and we hooked it up to an audio amplifier and put on the headset. And then we'd go down the lab, around the lab imaging and hearing what was going on. And we found out we could recognize objects. You could recognize a cube, or you could recognize a triangle. And got to the point where you could recognize faces by listening to that. So this is a synthetic sense, or what we call a transmodal representation of information. Same thing with the sensory prostheses. And of course, computer games. All of these things are what we call synthetic experience. They're technologically mediated. And we're closing the loop with these things. Now, this doesn't exclude our closing the loop with the outside world at the same time, not necessarily. Okay, now let's look at some of the dimensions of this synthetic experience. We're back to this taxonomy. How can we put some dimensions on it? Well, one of the things has to do with, basically that slice that consists of the sensation or the sensors. And we have these modalities we've already talked about, right? The senses, the external senses, visual, acoustic, haptic, olfactory, and taste, okay? We also have the other side, which is the action one, the actuators. The actions we take or the actuators what they take. So here we have movements of the body, speech, and even electrophysiological. As a matter of fact, a lot of the artificial limbs are electrophysiological now. You're measuring the myography, the electromyography of the muscle tensions, and using that to control prosthetic limbs. Have you seen this new, what's it called, the new band that goes around your arm? that's a controller now. It's we know about the LEAP controller in here. There's an optical thing. Well, this is a band that goes around your arm, and it's actually measuring your muscle potentials and things like that. It also has accelerometers in it, and you can use it as a universal controller. Use this band around your arm. Pretty cool. Okay, more dimensions. Now when we talk about space, because we have this synthetic experience, where is the space? Is it registered with the real space? Is it remote from the real space? Is it somehow distorted, like walking at the speed of light? Or is it miniaturized or magnified? In other words, are we zooming ourselves to where we're 1 millimeter high and we get a scale factor change in that space? Or we're macro. We make ourselves 1 light year big and then look at the universe from that perspective, or the Milky Way galaxy or whatever. This, by the way, is pretty cool stuff in terms of how it changes your perception, your experience. Then there's this idea of superimposition, especially when we're talking about virtual things that we're fusing with real things. Are these things superimposed over the real world so that they are, you don't see the real world, but you see only the virtual world? Or do you see the two in combination where you have the real and the virtual merged or overlaid? That's generally what we do with augmented reality. That was Mark's, Hirokato's invention, actually, is this video-based augmented reality. I mean, I've been doing see-through augmented reality in fighter cockpits for years with head-up displays and things like that, but this was video-based. Okay, then there's this whole issue of causality. This causality is, what are we causing to happen? What are we causing to happen, or what is happening to us as a result of something that's going on in the world? Is this something that's directly transmitted to us, or is it something that's recorded another time and is being played back to us, or is it something that's simulated? It doesn't exist at all in the world, but we're simulating it. And then, of course, there's the time factor. Same thing. Is this happening in real time? We can accelerate it, and we just see this all the time with television and sports programs and things like that, where we slow things down, and you get a slow motion view of what's happening. Did the guy really make a try? And we can do the snapshots, and we can completely distort time, as I mentioned, with walking at the speed of light. All right, so there's some more dimensions. I'll get to them in a few minutes, but let's stop there and go look at some of these other experiences. Okay, here's what happens when we have a recorded experience. In a recorded experience, generally our technology mediation senses it and records it. Now, it may do some filtering of it. Obviously, it's going to filter it depending on the field of view it has of the camera, if you're talking about a visual camera. And then we close the loop with a mediation. We play our VCR, right? So we're not closing the loop with the world. We're closing the loop with the technology mediation. Here is a recorded experience. Then there's also this whole notion of a transmitted experience. This is where there's some interaction in our technology mediation with the world, but we're not getting a direct connection to the world. We're getting it again through this machine. For example, let's say that we have an infrared sensor. It's at night. Infrared sensor basically takes the infrared spectrum and plays it back to us in the visible spectrum. That way we can see at night. That is a transmitted experience where the mediation is now filtering somehow that data and changing it. Here's another transmitted experience. This is a periscope in a submarine. So as you know, in a nuclear submarine or whatever, you have this periscope up here, and it's raised up so that you can be under the surface of the water, but your eyes can still see out, even though you're inside the sub looking at these things through this periscope. That is a transmitted experience. Here's another transmitted experience. Here's an M1 tank. And here is now a periscope in an M1 tank. In this case, it's actually an amplified view and filtered because you can see in infrared, and you can see at night while you're driving the tank around, things like that, and aiming the tank. And here I am in an M1 tank because I helped develop some of that technology that's in those tanks. Because the Army wanted to use some of my super cockpit stuff actually inside the tanks. Here, by the way, here I am in the driver's station of an M1 tank. You can't recognize me there, but let me tell you, that is so fun. You have the 50-ton vehicle that is like a race car. This is at Fort Knox in Kentucky in the U.S., and I drove this thing through mud holes and things like that all over the place. Scared the daylights out of the guys that were up in the turret, But it was so idiot-proof. I mean, it was like riding a tricycle. I mean, you have to understand these are Army guys. And so it was like a little tricycle that you would steer, and you have your speed control on it, things like that. But boy, would that thing go. And you have these two huge turbine engines that are running that, 50 tons. Anyway, that's a direct experience. What about a simulated experience? Okay, you see here, it's interesting. There is no connection to the world, but there is a model of the world. And what you're doing is closing the loop with the model. So that's where flight simulators come from, and where basically surgical simulation comes from. We've built 8 surgical simulators at the HIT Lab US that are, several of them are being used actually in surgical training surgeons as we speak. Some have been licensed by companies. One of the more famous ones of ours is the TURP simulator, transurethral resectioning of the prostate. This is what happens with old guys when they need to get reamed out, okay? So, mind you, I want my surgeon to practice on this a lot before he goes in and does anything to me, because it's really a sort of a ticklish operation that when you're reaming out the prostate, you want to be very careful where you're cutting, because if you cut too deep, you get the nerve endings. And in that case, you lose your will to live, for various reasons. And so what you can do is operate on these prostates, these virtual prostates, and you can most residents in urology, during their residency, when they're training to be urologists and do this procedure, may get an opportunity to operate on 50 patients, learning. And so most of those patients, of course, they have the real doctor, that's watching and things like that to keep these residents from really, causing a court case. But most of those cases are pretty much normal. But let me tell you, once or twice or 3 times in your career, you're going to run into an unusual one. So in the case of the simulated experience, the TURP simulator, you can do 50 procedures a day. And oh, by the way, you can put in all kinds of weird stuff happening. Put in bleeders where you hit a vessel and start bleeding, and it fills up your whole visual field. All you see is red, and you don't know where you are. And what do you do in that case? How do you irrigate? How do you get that blood out of there? How do you cauterize the vessel? All this kind of stuff. So they have to know how to do that, but they may not see that if they're operating most of the time. So this way you can simulate those things. Just like in airplanes, when you have an engine out, or you have a hydraulic failure, or something like that, you can simulate that so that pilots practice over and over and over again in the simulator, even though they wouldn't be able to do that in the real airplane. The same is true for nurses. These amazing simulated patients that have things wrong with them. You listen to their heart, get their pulse, hear them breathe, all this kind of thing. Look at their vital signs. They will talk to you, tell you where there's pain, all this kind of thing. And so you practice with these virtual patients, because it's tough to get real patients, that have all these problems to cooperate with these medical students. Okay, so synthetic experience, but there's some dimensions that we need to add here. And this has to do with, how do you get that model to begin with? Is it something you've scanned from the real world? Have we scanned this room and now created a three-dimensional model of this room so we can go into it again, change the coloring, change the draperies and all that kind of thing? Or do we construct it using some kind of toolkit? We author it, with some kind of 3D drawing program. It can be computed. Years ago, my students at UW were actually surfing on a mathematical equation. They created a virtual surfboard, and they were in this virtual world, and they created these different mathematical equations, and they were surfing on these things. That would be a computed model. There's also ones that are edited, where you're changing time. You're putting pieces from one piece from this location, another piece of this location, and putting them all together. And then there's all these data that have been collected, biometric, statistical, things like that, scientific visualization. All of that could be in this mediation. Let me tell you another story. So there's a physicist that was at the University of Washington, a good friend of mine. He was looking at the interaction of light and matter. He wanted to find out what happened when you actually change the bias properties, electrical properties of matter, especially semiconductor materials. How did that affect the absorption and reflection of light? So what he did was he came to me and said, I got all these data, reams and reams and reams of data, where he changed the biases and look at infrared light being shined on germanium junctions and things like that. And he said, I don't know how to make any sense out of it. He says, we have some theoretical models, but I'd like to see how this maps with the empirical maps with the theoretical and things like that. And I looked at the data and I said, well, let us play with it a little bit. So what we did was we built a model of the data. We actually built a planet that represented the data. The color, the height of the mountains, the water running around in it. There was this alien kind of planet. And so the data was coded. It was a sort of a scientific visualization coding. So I called him back to the lab and said, well, we want you to look at this. Look at your data, the way we've done it. And so we gave him a display, a monitor, and a joystick, and he says, you can fly around and look at your data. And he was doing that, and he said, oh, that's sort of interesting. And we said, well, would you like to go there? What do you mean? Would you like to go to this planet and be there? Can I do that? Oh, yeah. So we put on the headset, the data glove, and all this kind of stuff, and jacked him into the planet. And there he was, looking around inside his data. And he started saying, whoa. And he was moving around in there, and he said, well, this is interesting. These things sort of line up, and he is going underneath the ground and looking underneath at it and flying up high and all this kind of stuff. And then about that point in time, he started literally jumping up and down. His feet left the floor. He got so excited. He said, this is fantastic. And we said, well, would you like to see your theoretical equation superimposed over top of that? Well, yeah, can you do that? Yeah, we did it. So we showed him this equation. And he says, yeah, there's something wrong here. Wow. Well, anyhow, and the bottom line was he discovered a whole new effect that nobody had ever seen before. This so-called, and he called it the Pearsall effect. That was his name. And he He published it in the American Physical Society journal, and then they had the conference in Seattle, and he wanted us to take all that stuff down there. So all these physicists could see it and play in this world, and we did. And we had all these physicists jumping up and down off their feet. And it was the same data, but it was represented so you could make some sense out of it. And the only way you could make sense out of it is if you were in it, because humans are incredible pattern recognizers. And so that's what we did. So this model generation from various sources lets us do these things. Now, when we talk about augmented reality is sort of a special case here because we do have still the direct perception of the world. Now, in the case of video-based augmented reality, it's actually going through some device. But so we have the direct perception, but we also are sensing the world. Let's say we're tracking the tangible object, so we know where we're looking. And then we're inserting some kind of model into that. So when we're closing the loop here, we see the combination of the world and something that comes out of this box at the same time. For example, a head-up display in an automobile. That's really that's fusing two worlds together. Or in the case of repairing an automobile, where you're projecting the manual over the top of the motor, the engine, in order to know where to access data and things like that. And of course, the video-based augmented reality that the HIT Lab here has been involved in for a number of years. So what else is there? Well, there's one other thing here. There's the robots. Where do robots fit into this? Well, certainly robots can interact with the world, right? And certainly you can control the robots. But what's in between here is a model. Now, what happens? So what? Here is an example, robotic surgery. I talked about this before, didn't I? About robotic surgery. This robot, you see the robot here that's going to be over the patient with all these minimally invasive probes going inside. But here's a surgeon over here, right? And the surgeon has a head in this thing, manipulating this robot. And he can scale himself, scale his position coupling, where you move your fingers a few centimeters, and the robot will actually move micrometers. And so also you put a patient there who's you want to do a bypass surgery on this patient, heart bypass surgery. So you put them in there, and you put a few little slits in here, and the probes go in with a beating heart. And it measures the beating heart, and the probes are going like this. But the surgeon sees a still heart and is able to operate on the heart as if it's still, even though it's beating. And that's transformative. Then, of course, we have these robots that let us explore, like the new Mars exploration stuff. Now, the problem here, of course, this is not real time. As a matter of fact, this takes minutes. We make a command, and minutes before it comes back. But you can't really do that very effectively with that kind of time delay. So what you do is you close the loop with a model. You create a model, you close the loop with a model in real time, tune what you want to do, and then send the command. So then you get the rover where you want it to be. Okay, you with me so far? All right. So that's a taxonomy. Well, let's look on more about the some of the technology aspects, and especially how it relates to the human. We talked about the human, that we have now concentrated on that. We've talked a little bit about the machine and the introduction of the technology. What about now looking at some of these layers, the machine side of the layers? Now we have 3 layers there too, don't we? Just like the layers here, where we had the sort of the sensory level, this is transducers. We had sort of the organization of the signals going to and from the transducers. And then finally, we had the cognitive piece of it. And then what goes back and forth here are signals, photons, mechanical vibrations, whatever. So let's look at some of the definitions that relate to these levels. Okay, by transducers, pretty much what transducers do, as we talked about before, is transform signals from one form to another. For example, electric audio signals to sound vibrations using a loudspeaker or headphones. That's the transduction level. And then we have the next level, which is the signal processing level. This is where we're actually organizing these signals, manipulation of electrical signals to achieve objective, like creating a binaural sound or creating a raster of electron beam to actually eventually create a picture. But then we get down here to the bottom, what is maps to the cognitive side, and that's the program. The program is the plan or script that manipulates all those things so that you get a concert or you get a movie or you get whatever. That's the actual content that is in the device. Now, there's some other things that are important, especially when we talk about interaction with humans, and one is the bandwidth. This is the rate at which the data can be transferred through a system or between systems. Clearly here we're interested in the bandwidth between the human and the machine. But then there's also this notion of compression. Compression is tricks that we can play because there may be redundancy in that information path. And we can eliminate that redundancy, and as far as we are concerned, we still get the same amount of information. Well, that may or may not be true. Let's take, for example, music. Music nowadays pretty much is digital. Everything is digital. It's sampled at 44 kilohertz, right? You look at the Nyquist limit in terms of the maximum frequency you can get with 44 kilohertz sampling, and that's about 20 kilohertz. And they say, well, that's the limit of human hearing, that you can't hear anything more than that. Well, as it turns out, you can, but you don't know it. Because if you play a person a digitized music that has this bandwidth, and then you play them an analog version that goes way up in terms of, can transduce up to 40, 50, 60 kilohertz. You ask the person, well, if you play the tone path, it craps out at 20 kilohertz. But you listen to the music and you ask them, well, which one is different? I mean, and I say, well, this one over here is different because it has more presence in it. It seems to be more real. That's because you're actually hearing stuff that you're not necessarily bringing to a cognitive level, but it's all subconscious. We have an amazing capacity that we never bring to a conscious level. One of the things we found in a system we built, we want to look at what was the workload for pilots in the cockpit flying. This time it was in B-52 bombers that were flying at low altitude, about 500 feet over the ground. This is a big bomber that's flying really low, trying to get underneath the radar. And raw workload. As a matter of fact, there's a lot of ground buffet and things like that. You're just shaking like crazy while this is going on. So we wanted to find out what workload these guys have. Well, it's sort of tough. How could you come up with an objective measure of workload? Well, there's something called a steady state evoked potential. Steady state evoked potential is actually pinging the brain with light and defining out what processing is going on. And so we would do that with this flashing light up here, just in the periphery. And it would sit there and flash at about 60 to 70 hertz. Now, generally the critical flicker frequency is a lot less than that, where you fuse it into one thing. But we're actually seeing brain waves at those frequencies, which means that that signal was actually being processed and picked up, processed through the sensory end organs and going up to the brain, because we're measuring with electrodes on the brain. And so there's so much capacity that we have that we don't realize that we have. So we use that. We looked at steady state volt potential and tell how hard these guys are working by probing the brain that way. Okay, so there are two aspects of this pathway. One is that goes toward the human. That's what we generally call displays. And the other one is what comes back, which is what we call controls, as far as the machine side are concerned. So here we have the machine side with generally the displays we think about, visual, acoustic, tactile. There are others, olfactory and so forth. And then the controls, movement, sound, and so forth. And that's mapping this same picture that I showed you before with the direct things. But we also have all these indirect connections that we've seen before. Okay, so what kind of machines do you build? Well, you ask the question, what is it supposed to do? One of the things I tried to get someone to do is I had a problem. Well, how do you see at night when you're flying an airplane at low altitude and high speed? So here was the problem. We had all these amazing sensors we could put on the airplane. We could that would amplify light or look into an infrared spectrum, things like that. But the way we represented it, this was in my lecture I asked you guys to watch. One of the problems was that screen was so small that you couldn't see the picture elements because we couldn't make it but so big because of all the other instruments in the cockpit. It would take up too much space. It would crowd out all the other instruments that you need to have. So this was the problem I was trying to address in developing these cockpits. And so I started looking into this whole idea of virtual images. It turns out that's where the term virtual reality comes from. It has to do with optical physics, the idea of a virtual image. A virtual image is an image that you see at a particular place in space that doesn't exist there. When you stood in front of the mirror this morning, what you saw was this reflection of yourself. Well, you weren't really on that other side of that piece of glass, but you appeared to be there. Actually, that's not what you look like. You know that? You don't look like that. That's a mirror image of you. You need to see a proper television picture of yourself because you're switched around. But you saw this reflection of yourself, so that was a virtual image. Here you see real clouds and virtual clouds. Trees are not growing down, they're growing up. So, how could we use this idea of a virtual image to solve the problem of how to see at night? So here's Lieutenant Furness wearing the world's first helmet-mounted display. This is where you're now taking the information from various sensors in the aircraft, and you have a miniature television picture tube here in magnifiers and collimators, and you're looking down this barrel, and what you see now is a picture that's this big instead of this big. And so you take information from these various components on the aircraft, missile seekers, computers, radar, all this, represented on this miniature television picture tube through some kind of optical mechanism, and now this picture becomes this picture. So now you aren't even taking up any cockpit space. You have a black box back in the airplane that runs this, but you have this small device on the side of your head. It sends up the image. Now, one of the problems at the time is this is a cathode ray tube, and there's about 15 kilovolts sitting there on that cathode ray tube on the side of your head, which means that you want to be careful about that. And oh, by the way, if you ever have to eject or get out of the aircraft in a hurry, and you pull that cable apart, you want to make sure that you don't cause a spark, because that could ruin your whole day. Now think about what I've shown you. I showed you before Remember what I showed you before with the magic helmet? What was that? The first week. What were we doing with the helmet the first week? Wow, I'm making a big impact, aren't I? You remember this?
Using it to direct me what it's child.
Aiming. And what is this?
Slow.
Yeah, so what happens when you put these two together?
Long place on the head.
In addition to that, we've solved that problem, but
Use one or
what do we call that today? It's virtual reality. Now here it is together. Here's the infrared tracking system, and this is a paraboloid on the visor. We take the cathode ray tube on the back of the helmet, send the image up over the top of the helmet with a coherent fiber optic bundle, bounces into the visor, into a central mirror located at the focal point of the paraboloid, back in the visor in the pilot's eye. So you have this clear see-through display, but when you switch it on, you have this visual display that's out there. Now what happens is that picture you can move around. So now as you're moving your head around, the sensor tracks your head position and you see through the cockpit wherever you look. And oh, by the way, you can put data on top of that. And what I'll talk to you about next week is a super cockpit, where you create the whole cockpit that you wear. But that comes a little bit later. But think about what's happening here in terms of the impact of the human. This whole business of the bandwidth, which we decided before was a function of all these things. All right? Now we can do this virtual reality different ways, this virtual display. This can be occluded, where you don't see the outside world. It can be see-through, where you actually see the outside world and the projected world, or it can be multiplexed, so that you are able to look in one direction to get one piece of information, the other direction to get another piece of information. The Google Glasses right now are a see-through kind of display, but they're a see-through multiplex display. So you generally want to keep it out of the way of your direct vision, and you look up in order to see the information. So, but you can also play some other tricks with virtual images. Okay, so here is, well, let's call this, for argument, a real image. What I did is I took my camera in front of me and I snapped a picture looking straight on, okay? So that is a real image. Now here is a photograph I took of myself holding the camera and taking a snapshot of me standing in front of a mirror, right? So that's a virtual image, right? You with me? This is really not what I look like. This is a virtual image of me. Okay, now I take another mirror and I hold my camera into this. And now I take a virtual image. And then I do this, and I take a virtual image. It's really neat when you go into VR and you stand in front of a mirror, what you can see in that mirror. That's right, what you want to do in it. So, again, definition of virtual image is not just optical. It can be an auditory or a tactile, olfactory even, which are transmitted to the sensory end organs such as they appear to originate within the three-dimensional space around the user. The magic word is appear. They're not really there, but they appear to be there. Now, in the early days of when I started the HIT lab, after I'd been doing all this work for the Air Force, I decided people needed to know what virtual images are about and to have the ability to experience for themselves this. So one of my early patents, this is 1992, was the very first commercialized head-mounted display. This is why Google's infringing on my patents, you know, although this patent is about ready to run out because it's Google, it just took so long for Google to shape up, you know, that. So here it is. What it consists of is basically a liquid crystal image source up here, rear illuminated by a vacuum electrofluorescence element. It shines down onto a prism or a toroidal mirror, and then when you look down in that direction, you see a virtual world. It's like getting a 1 meter screen at about 3 meters away. And so this is what the device looks like. Again, this was built in about 94. And here's a person wearing it. So you have a television receiver here and the battery pack, and it goes up here and turns on this display. So that what you can do is be sitting on Waikiki Beach watching the NFL football playoffs at the same time. Why would you want to do that? I don't know, but you could do it. You know, the technology allowed to do it. Well, as the story goes, we raised a lot of money. We took it to the Consumer Electronics Show. People lined up for 2 hours to see this thing. They said, this is transformative. I mean, this will change the whole world and all this kind of stuff. This is in 94, remember? Gosh, that's almost 20 years ago. Isn't that right? Yeah, 20 years ago. Golly. And then we ramped up for production. We raised a lot of money, ramped up for production. I had the production line going, cranking these things out. And they were introduced into the marketplace. The first place was in Seattle at Magnolia Hi-Fi. And people, again, it was all in the news. They showed up. They were waiting outside to see it. They'd come inside, and they would put these things on and be able to show videos or whatever. And these are mostly guys. And they said, I gotta have these. When can I buy some? We said, yeah, you can buy them. How much are they? $799. Ooh. $799. Now, we didn't know at the time. This is where our focus groups failed us. This is where your marketing becomes so important. The technology was expensive. Those little liquid crystal screens was in the early days. They were really expensive. Our margins weren't that great on this thing. And so we found out that the break point was $500. At less than $500, a guy could go buy these things on his own without consulting his partner. But if it went above $500, guess what? He had to go ask his partner. You can imagine how that conversation went. I really saw these glasses I like. I mean, they're really great. And I didn't know you have problems with your eyes. Well, it's not those kind of glasses, and so you can see what happens. It costs too much. And it was a bust. Except for those kids. Did I tell you about that? I didn't tell you about that. That comes, I guess that will come to next week. The other part of the story here, which is sort of interesting. So we were a little bit ahead of our time because all we could do is use broadcast television or plug into a VCR. Guess what didn't exist at that time? DVDs. So, you didn't have a medium that contained movies and things like that. Now there's a DVD. Sony comes into the game and says, we build the Glasstron. The Glasstron will give you this, like being in the theater. You don't have this small screen that you have in your DVD player. You're like in a theater. So they built the Glasstron. It didn't go very far either because the quality wasn't that good. The image quality wasn't that good. Then Imagine comes along, another Seattle firm that started taking advantage of some of the things that we were doing. And they're still in existence. They've come up now with OLEDs, or organic light emitting diodes, which give you a lot more luminance and higher resolution. And then finally, a company comes along like MyView that allows you to buy these for $199. Same technology. And you plug this into your DVD player, and now you're in a theater. And you plug it into your iPad, plug it in an iPhone, your iPod, and these are sort of granny glasses kind of things, so you can see the outside world, and you look down and watch the movie. So this is an optical multiplex kind of display. If you want to model, as I mentioned, it costs a little more to come well with it. So that's technology that does get closer to matching what humans do, but not nearly far enough. The whole object here is to take some kind of image plane, object plane, that is a source of pixels, and then relay that to the eyes. That's what we did in all of these optical devices, all these head-mounted displays before. So here you have some kind of object plane with all the pixels in it through optics that eventually relay that picture to the retina of the eye. That's the way most head-mounted displays work. Matter of fact, that's the way that the Google glasses work. But the problem with that is if you want to make it a big picture and you want to make it high resolution, that means you have to have a lot of luminance and a lot of pixels. Otherwise, you have empty magnification. You see all these blobs. It's like being legally blind going into a virtual world. But what if you could take one pixel and move it really fast and modulate it while you're moving it in both color and in intensity to paint the picture directly on the retina where you aren't starting off with an image plane to begin with. All you're starting off is with a photon beam. Then you would have what we call direct retinal projection. And there is no image anywhere except on the retina of the eye. And that's one of my patents, called the virtual retinal display. It was patented in about 92, 93 time period, 94. And the idea is it's a display breakthrough. Nothing like it ever before. And so you now do away with the computer screens, you do away with projection screens, you do away with newspapers, movie theaters, things like that. Image goes directly. The photons go directly to the retina. This is the largest project that was ever done at the University of Washington. We licensed this to a company called Microvision that still exists, and still making them, for $5.133 million with a royalty of 2.5% and a 9% equity interest in the company. We were a cash cow for the University of Washington doing this. This is one of the 26 companies that we spun off out of the Hit Lab. Okay, let me play you this little video.
Now, we've all seen pictures and text on computer screens like these, but what if I told you that over in Seattle, they're working on a laser system which bypasses the screen altogether and projects a high-resolution color image straight onto the retina of your eye. It sounds unbelievable, but they've already completed a working prototype. Craig Doyle checks it out.
This is the first full-color virtual retinal display, or VRD for short. The way it works is, instead of seeing the image on the computer screen, it's painted directly onto my retina by a laser. Now, I know that sounds a little bit dangerous, but the laser is quite low powered, so it won't damage my eye. What I do is, I line up one eye with a little colored dot I can see. Now, as I move in, the picture gets bigger and bigger and bigger as the dot expands, and then there, I can see the full picture. Looks like it's hovering in the air about 5 feet in front of me. And it's exceptionally high quality. The flickering is caused by interference with our camera, not the VRD. In fact, the VRD goes one step further. Not only can you enter a virtual world, but let you overlay those images on the real world. Now, the incredible thing about VRD is, because the image is put directly onto my eye, there's no need for an intervening screen. So if I lift this up, Right, now I can see the picture. I can see everything else in the room as well. So if I just slide my hand in there, now it looks like the whole picture has been superimposed on my hand. It's fantastic.
They've already let you superimpose information on the field that we're working in. You could think of it as being able to superimpose the map of this patient's anatomy directly into the surgical field. And the VRD lets you do this because you can see through the display and into the patient.
If you watch neurosurgeons, for example, if you look around here, you see a backdrop of all the information that they have to look up and take a look at. You have information about the spatial location that they're actually in that you got from previous MR or CT data. You have information they're getting out of the surgical microscope. You have an enormous amount of physiological ancillary data that you have to monitor, like blood pressure and pulse oximeter. And if you watch the neurosurgeons, like he's at a tennis match, he's looking down at his hands, he's working, and he's looking around back and forth to get all this information, which leads to fatigue. It's going to allow neurosurgeons to get all that information that they need and stay very comfortable.
In the field of
So this one guy came into the lab. He'd heard about the VRD, and I don't think I told you this story, did I? That's it. And we put him in an optical bench. This is in the early days of the VRD. We just had the optical bench set up, and he had heard about it, and he wanted to see it for himself. So we set him down at the optical bench. At that time, it was just it was a red display, just a single color. And we had this ocular you had to look through where the image would be painted on your retina. So he came in and he looked at it and he said, "Wow, that's really amazing." And we said, "Well, just take off your spectacles because you don't need your spectacles for it. You know, you see it just as clearly without your spectacles." So he looked into it and he said, "Well, yeah. It's pretty good." And then on his own, he happened to look with his other eye, and his mouth, his jaw fell open, and he said, "Wait a minute, what are you guys doing here?" And he says, "I'm blind in my left eye, but I can still see that image as clearly with my blind eye as I can with my good eye." We said, "Oh yeah." And it turns out he'd been in an automobile accident that left a lot of scar tissue in his eye, and apparently that was his retina was still working, but he couldn't see out of that eye. We're getting through that, and went over to the Department of Ophthalmology at the university, and they started sending patients to us, and sure enough, these patients, this was working with patients who had all kinds of vision problems, and that set us on an entirely different objective that we're working on. We're in the low vision and using this technology. So it's one of those things that can be a universal technology, a lot of use in the military, a lot of use in maintenance. And oh, by the way, it's interesting that this is our projection of what it was going to look like back in about in 2000. And this is, of course, what the eyeglasses look like today. So the Google glasses are nothing new, you know, is the whole idea. There's Mark wearing the new set, right? And then, of course, you can go in that other direction, too, with Toshiba and what they think they ought to do. Okay, gang, that about does it. I have an assignment for you for next time. Here's your assignment. There's a guy by the name of Randy Pausch. I don't know if you guys have ever heard of Randy Pausch. He was a computer science professor at the Carnegie Mellon University. He did what you may have heard of in the past called the last lecture. And this lecture is not about computer science. It's he was a virtual reality pioneer as well. It's about life and about how you need to get all out of life that you can. Because he died with pancreatic cancer, left 3 kids and a beautiful wife. I knew him, and he was a great friend of mine. And in the last lecture, when you actually watch the video, it's about an hour long, he talks about the day that he met me. and I was giving a keynote address at one of the conferences he was attending. So you have to listen to that and hear what he had to say about that experience. And after that, we got to be really, really close friends. Last lecture, something you need to launch you through the rest of your life. Okay, any questions?
So that was the
You want us to watch it or read the book?
I want you to watch it. Watch the lecture, the last lecture.
My question is just why are we using this physics classes? They're pretty crap.
Why are they what?
Why are we using this? No, that's physics.
Oh, yes, they are. Well, I mean, the real issue in all of these things is the economy of scale. When you're able to make a lot of things, the price comes way down. One of the biggest problems in the virtual retinal display is the scanner. And Microvision, the company that spun off, I actually gave it its name. I wrote the business plans for it and all that kind of stuff. It's the scanner that we built for it originally made by hand. Well, it turns out it was difficult to do that in quantity, make it that way. So we decided to go for a MEMS device, a micro electromechanical machine that's really made using silicon foundry kind of technology. And it took us quite a while to get that working. But now it is, and it's a 2-axis mirror. It actually scans, one mirror that scans in 2 axes. And it works pretty well. And I'll bring it in next time. It's also the foundation of a laser projector, a small laser projector called a pico projector that also came out of Microvision. But that's the reason that things cost so much. To get it to the point where you can manufacture it, then you have to amortize all that cost that went into building that. The virtual retinal display, to me, is the way to go. I mean, it's just, you can get so much more luminance, more resolution, everything with a VRD than you can with any kind of array technology, any kind of matrix element array, like OLED or liquid crystal.
What's the range and the resolution like? I've noticed you had to go quite close to the mirror to get it into the right. Could you say have it on the other side of the room and it track your eyeballs so that when you move around it'll keep on projecting onto you?
Yes, you can do that. We haven't done it, but you can do that. It was one of my students, a PhD student, one of the was contemporary with Mark, actually worked on some things like that, where we not only were scanning the image on the retina, but we were determining what pixel you're looking at. So we're actually determining where your eyes were located, as well as where your whole head was located with that same thing. One of the applications that we also investigated was you have this problem with a small screen, right? What if you held it up to your eye like this? We can make you a screen this big. And then because of this eye tracking thing I'm talking about, we know what pixel you're looking at in that screen, and then you use speech to select or button. You look at something and select it, or say select, or give some kind of verbal command. This way you now solve the problem of small screens. You have the huge screen, color, bright, it didn't matter. You can see it at bright daylight.
You have the N-gauge problem again.
Sorry?
The Nokia N-gauge problem.
The N-gauge.
You have that problem again.
What then?
You talked about it the first lectures.
Oh.
You hold it in front of you.
That's right. But what if you're blind, have low vision? Okay. Furthermore, we're looking at the retina, and we get reflected energy back from the retina. We can tell whose retina is actually getting the picture, so that you don't get the picture unless it's the correct retina. So it can be secure using a mobile device. Yeah.
Do you foresee that laser prediction technology getting smaller to the point where you can mount it?
Well, you can mount it now. I mean, all the events now all the systems now are, super lightweight and things like that. But they're still expensive, very expensive. Military buys them, you know, but yeah, that's the problem. Is they're too expensive. I mean, you're still talking about, you know, thousands of dollars rather than a few $100s. But again, with economy of scale, it could get down. I mean, you can run these things on a hearing aid battery because you use every photon. You're not throwing away any light. All this light up here, you're only getting a fraction of that light. You only get a fraction of this light. Only a few of the photons coming in. It's spraying photons everywhere. Very inefficient. Whereas with the VRD, you're using every photon. Very efficient in terms of light husbandry. Yeah. I mean, way low power. We're talking about energy levels like in the video that we're talking about, you know, like the amount of photons you would get going outside in the daylight.
Natural light.
Mm-hmm. Yeah.
Do you come across the problem with not so you've sort of overcome the resolution issues for the projection of it, but do you have problems with the generation of data at that kind of resolution? So like getting videos, it'll be at that resolution, or
Well, I mean, what you do is you can watch movies with it and things like that, but eventually you run into a pixel flow problem that you just can't pump enough pixels. The bandwidth becomes the electrical bandwidth becomes an issue. You can make this picture really big, you know, put as many elements as you want to, assuming you can modulate the beam that fast.
Yeah.
Assuming that you can, then the pixel flow is a real problem. And that's why I talked about bandwidth and streaming bandwidth, where people are running around with these devices on their head, you know, it's going to bring down the system in a hurry.
The computer displays normally, it's got like 1 pixel, like 320 that way, 240 that way. But the BRD system can almost completely ignore the fact that it's in that sort of matrix.
Well, that's in terms of the physical components, yes. And so you aren't having the switching problem, you know, allocating between the different picture elements. But you do have this problem of that beam is moving really fast because you have to have it above the critical flicker frequency. And you can make multiple beams, you know, and things like that to make it easier. But the bandwidth issues can be very high if you're talking about, you know, 3,000 by 4,000 picture elements. 12 million picture elements that you're refreshing at 60, 70, 80 times a second. That's a lot of bandwidth pumping down there. Yeah. Now also it scans both directions. That's another thing. You're painting the picture in what we call a booster photonic pattern as the ox plows. We're actually painting the image this way, and rather than a raster, you know, which most TV does. When there's no flyback, you know, you're just
Those lights skipping or anything.
yeah.
With the audio example you gave before, the range, say you get an audiophile who says they can perceive more elements of the audio. Do you have any comments on that?
Well, I mean, there's some research that talks about this sense of presence with artificial reproduction of music, and this whole thing of harmonics that if you don't have the bandwidth that samples or reproduces those harmonics, something is missing. Something appears to be missing, and that's apparently it's these harmonics that gives the sense of presence of the music. Case in point, I have you know, probably the best recordings you can get on CD of various symphonic music, like the planets. The Holst's The Planets is one of my favorite ones, and especially some of the And even the best recorded quality doesn't even come close to being there. When you're in and have good acoustics, I heard the Birmingham Symphony Orchestra in Birmingham, England. And they have a new concert hall, new symphony hall, which is acoustically is just beautiful. And I had a great seat there, and that was the most stunning performance I've ever heard. I didn't think music could sound like that. And you could hear every instrument and the sweetness of the violins and everything. You never got that on any CD that you're playing. It just isn't there.
Is there an element where people kind of make up the sound in a way? Like, you know, you perceive something and then your brain reproduces it so you can perceive it.
Well, I think we do that all the time. I think we do that we listen to music and we think, well, we think it's all there until we hear something that we make the side-by-side comparison. Yeah. Well, and the same was true with TV. I mean, before high-def television, you know, even when we added color, everybody was remarking how much more I can see with color, you know, that I can see blemishes on the face and hair and things like that. But then when the high-def happened, you know, you don't realize how much you're missing until you see that difference.
You, James, was talking about the old video cameras they had. So basically they'd record an analog video, but these days they record in like 1080p, which is full digital. So those can't actually reproduce.
No.
Full
No, the old video cameras aren't even close. The analog cameras can't compete with the digital ones because they were really old technology when we didn't even have a 1080p standard. But you could. Electrons are really small. As a matter of fact, in that first, well, you haven't seen the Darth Vader thing yet, but in the Darth Vader thing, we were scanning 1,200 TV lines. And this was back 20, 30 years ago on miniature cathode ray tubes. Electrons are really small, and you could do some wonderful things with them. And but we didn't have the standard, the television standard, the NTSC standard wouldn't let you do that.
I think they're currently re-recording the analog videos to facilitate higher than.
Yes, they are. Yeah. Well, and the audio, it's interesting, there's a bit movement now back toward audio amplifiers, analog amplifiers, back to vinyl, back to things like that, because you can capture some things there that you can't, even though you have a lot of noise and things like that that comes along. Still, there's some elements that are missing. Interesting thing, too, about amplifiers, vacuum tube amplifiers. The old Macintoshes and Marantz amplifiers and things like that are vacuum tubes, cost a fortune, but they're on their way back because vacuum tube amplifiers produce, and their harmonic distortion, even though there's not much of it, produce even harmonics, whereas Class C amplifiers using solid state generate odd harmonics and harmonic distortion. And so that's a difference in the way it sounds. And going through transformers and things like that, you know, it's a lot softer. Analog music is sort of, it's not as harsh, perhaps.
My friend's a musician, he says it's warmer.
Warmer.
Yeah.
It's not as harsh.
He's gone back to old.
Yeah.
Gone off the digital amplifiers and back to the analog stuff.
There are a lot of people that are doing that because it's just raw, you know, and this is, you can't, you know, if you look at the spectrum, you do a spectrum analysis of it, you say, well, you can't hear those things anyway. But you can, you know, that's the point. You know, you're really hearing things up here that we didn't realize.
There's some audio file thing where if you are sort of tuned into that, you'll basically see that. And if you hear something that's not there,
Yeah.
you're like, this is
Yeah, but it takes a trained ear to do that. I mean, most people, you know, listening to things through their headset from an iPhone or something like that, don't even know what music is, you know, because It's such low quality. Yeah. Okay. Okay, great, guys.